So we have been discussing about different advanced surface characterization techniques for the last 4 or 5, even more 7 lectures. So the last technique which I am going to discuss in detail is known as secondary ion mass spectroscopy. In the literature it is always written as SIMS, being the acronym for secondary ion mass spectroscopy. This is very advanced technique and very few laboratories in India have access to this technique. As far as I know, only the laboratories access to the atomic energy like BRC or IGCAR, they have access to these facilities. But still, for the understanding of different students, we need to discuss this technique in detail. The literature is very well known in these topics. The most important book on which literatures are available I have listed at the bottom. First one is by J.C. Wickerman. Second one is again the Encyclopedia of Material Characterization, edited by Bundle and Evans and Wilson. These two books are easily available in different libraries, so you can have access. The outline of this presentation is as follows. First, I am going to discuss about historical background of SIMS, but before I discuss about historical background of SIMS, I must talk about the mass spectroscopy per se. Then I am going to talk about the difference between the MS and the SIMS, and most notably what are these two techniques are, so that you can get a feeling of mass spectroscopy and secondary ion mass spectroscopy. Obviously, these two techniques are related. Followed by, I will discuss the working principle of both the techniques, and then I am going to talk about different measurements which can be done by SIMS. Also lastly, the advantage, disadvantage and some amount of instrumentations. As you know, it all started in about 110 years back by Sir J.J. Thomson, who first basically built the prototype of mass spectroscopy to measure the m by z of any electron, mass by species charge. And as you know, he was awarded Nobel Prize in 1906 for his discovery and for many other things which he has made. But basically the first concept of mass spectroscopy came into practice by a gentleman known Francis Aston, who was working in Cambridge in England, and he actually first principle or concept of mass spectroscopy was put forward into practice by him, and he was also awarded Nobel Prize in the year 1922. Then it saw a huge effort to make the mass spectroscopy popular. Different kinds of mass spectroscopic techniques came into picture, but the real problem in dealing with mass spectroscopy was the vacuum systems. In early 20th century, basically 1910 to 1930 and 1935, the vacuum technology was not so well known. So the technique has not progressed much. Only in 1948 to 52, in the post Second World War era, the important time of flight mass analyzer came into picture and changed the scenario. It was followed by a major discovery again by W. Paul, which led to quadruple ion filters. And this quadruple ion filters actually has allowed us to measure this PCS of different mass by Z value, m by Z values, and because of this very famous discovery in 1955, W. Paul was awarded Nobel Prize in 1989. Actually, he also invents ion trap in 1983 for informations. After that, in 1968, it saw the development of tandem mass spectrometers, and secondary ion spectroscopy came little later, at about 1980s, when the secondary ions production was possible by different primary ion sources. To give you a better idea of SIMS, the most important problem in developing SIMS was the pumping technology, vacuum technology, as I told already, and that's actually hindered the growth of these SIMS. In fact, only in 1940s, actually 1948 or so, the first prototype experiments in SIMS was done at University of Vienna, Austria. In 1960s, two SIMS experiment was developed, but not so good. One was an American project for analyzing moon rocks, other was at the University of Paris. These first experiments were based on a magnetic double focusing Richter field mass spectroscopy and used argon as a primary ion beam. Obviously, these things are not known to you, I am going to discuss in detail. And then this was followed by recent development on focusing these noble primary ion sources, physicists like C60, even ionized clusters of gold and bismuth. And this followed a lot of instrumentation and the computation of the technique, and now it is fully automated and comes at a cost of about few tens of crores of rupees. Well, what is actually mass spectroscopy? That's you must know first. Mass spectrometry or mass spectroscopy is basically an analytical technique as any spectroscopic technique, but it measures a different thing. It measures mass to charge ratio of any charged particle. You must remember this. Any mass spectroscopy does not measure mass, it measures mass to the charge ratio of any charged species. So therefore, in any sample, whatever material you think of, there is no charged species because samples will be neutral. You need to create the charged species first, and then by using certain technique you can measure this mass to charge ratio. This is a characteristics of any charge, whether it is a single ion, single atom ion charge, or it is a multiple ion charge, multiple species charge, does not matter, but this is a very characteristic things. It have used in both quantitative and qualitative analysis to determine the composition, also structure of specific compounds. Not only that, it allows us to be used as an analytical method to measure the molecular and atomic weights of the sample. So it has a versatility, as you can see. It gives a host of informations, and I have listed only few of them in this slide. First and foremost, it allows us to determine the chemical and structural information of any molecule. Any molecule or any ionic species you see, it gives us an understanding of chemical and structural nature of that molecule. Then it allows us to identify the unknown compounds to start with. It also allows us to quantify the known compounds. We can actually determine the relative abundance of isotopes and measure the exact masses. Remember, it is possible to measure the exact mass of the isotope. Those masses you see in the books reported are basically measured using SIMS. And then it also allows us to measure the molecular mass of any sample, correct. Now if you look at the uses, it is used in wide spectrum irrespective of different branches of science and engineering. Most important one, it is used in geological problems, basically in oil consumptions or oil production units. Like in oil production unit there are different kinds of chemical species available, organic, and it allows us to detect them. Then comes the pharmaceutical industry, that is pharmacokinetics, drug discovery, drug mechanism. Next one which uses this technique extensively is space application, like composition of the plasmas and the solar winds by the astrophysicist. Obviously it can be used for environmental technique like water quality, food contamination, biotechnology. In fact, it can be used in high vacuum system, smart spectrometers to be used to measure even residual gases present in a particular systems. If you look at this series, I have not mentioned about materials science. So obviously material science is involved in all these things. We can use this particular spectroscopic spectrometry technique for analyzing our day-to-day materials or the materials which you are actually preparing in the labs in detailed manner. Well, so basically after knowing this mass spectroscopy and the advantage and that these things, what actually a mass spectrometer needs to have? What are the basic things it must have? Well, basically it must obviously have a sample, because that is what we are analyzing, and then we have to have a source of ions. So sample is ionized and we create different sources of ions. This is what is done by these techniques, which I am going to discuss. And then these ions are actually analyzed based on mass to charge ratio by using either quadruples or time of flight measurements, and then they are detected either a photographic plate or electron multiplier or Faraday cup, or different kinds of detectors available. And the whole system, whole thing is kept, this whole thing has to be evacuated, because the ions needs to move forward from the source to the detector. So their movement should not be hindered by any kind of residual molecule, gaseous molecule present in the system. So vacuum systems to be of the order of create a vacuum of the order 10 to the minus 9 to 10 to the minus 10 torr inside the chamber, and this all actually leads to the cost of the instrument. So this is the basically 3 modules of any mass spectroscopy. In SIMS, both the analyzer and detector remain same, only thing which gets changed is the source. We do create secondary ions using the primary ions, okay, but in a mass spectroscopy we use primary ions to analyze these masses. So in a nutshell, if I have to show you in a very chart, what you need is to create ions, and this can be done by ionizations. You can do by electrospray, you can do MALDI, I will tell you. You can do even other ionization techniques, like you can use a primary source of ion, a sputter, and create ions. And then after you created the ions, you have to collect the ions. You collect the ions and then you separate them in a different mass to charge ratio. That is what is done by mass analyzer. It can be MALDI time of flight, or it can be quadruple time of flight, it can be quadruple time of flight only, or you can be triple quadruple also. There are many others actually, but these are the main ones. After that, we will detect the masses, and that is done by mass spectrum analysis. Also you need to have a database, like X-ray diffraction has a database and many others. So this is the main thing of a mass spectroscopy. Only thing, as I said, is going to change in SIMS is basically this part. These 2 parts, other 2 parts will remain same. So actually you create an ion source, you can have a gas ion, mass analyze and detector. This is what I have told. So in a basically pictorial things, I can say there is an ionizer and there is a mass analyzer, there is a detector. That is how the ions actually move through this. How do you ionize actually? That is what we must know. There are different ways of ionizing. First one is known as fast atom bombardment, or FAB. This is nothing but impact of high velocity atoms on a sample dissolved in liquid matrix. If you have a high velocity atoms like argon or oxygen or cesium, and these atoms actually are allowed to fall on a sample which is kept inside liquid matrix, it can create ions of the atoms in the sample. Second one is secondary ion mass spectroscopics, and this is the topics of today's discussion. It is nothing but impact of high velocity ions on a thin film of a sample of a metal on a metal substrate. It can be also dissolved in liquid matrix. So by this way, these fast ion bombardment and secondary ion mass specs, actually the preparation of ions are almost similar. What you need to have is impact of the high velocity ions in case of SIMS, and in case of fast FAB you need to have impact of high velocity atoms. Then you can always have a plasma desorptions. This is nothing but impact of nuclear fission fragments. Nuclear fission fragments are always like alpha particle, gamma particle or beta particles. These fission fragments can lead to plasma desorptions. You can also have a technique known as, so we have discussed this, we can also have a technique known as matrix assisted laser desorption and ionization, which is known as MALDI. That is what I talked in the last slide. So it does actually create ions by impact of high energy photons on a sample embedded in a solid organic matrix. So, you create a photon is nothing but h nu, with laser has a lot of photon or quanta, and this is basically allowed to fall at a high velocity on a sample which is embedded in a solid organic matrix, and that is how you can ionize ions. Then one can do field resorption on electrospray. Field resorption is nothing but imposition of high electrical field gradient on a sample deposited in a special solid substrate. Those of you who have some idea about atom probe, in an atom probe we do the same thing actually. We just create a large, we impose a high electrical field between the sample and the electrode, and because of the creation of the high electric field, the ions on the sample is just dislodged, or the atoms in the sample are dislodged and created comes as an ion. Electrospray is basically very simple, much simpler than all these techniques. It is nothing but a formation of charged liquid droplets from which ions are desolvated or dissolved. You have a charged liquid droplet, you can create charged liquid droplets by using electrical field, or just spray using electrical field, and then you can dissolve it or dissolve. So, these are the different techniques of ionizations which is done. So, you see SIMS comes one of the techniques of ionizations, not only SIMS, there are many other techniques. So, that is why I want to discuss mass spectroscopy in togetherness. Now, how do you then, after creating the ions, you have to analyze the masses. How do you analyze the masses? There are host of techniques available, that is what the discoveries happened. First and very simple one is single focusing magnetic deflection, which I will tell you. Second one is double focusing magnetic analyzer. Third one, which is widely used, is quadruple mass analyzer. Then you have mass analyzer, and the last one, which is very popular one, is known as time of flight mass analyzer. Let us look at them. This particular slide is on single focus mass spectrometer. This is very simple technique, very simple technique. This picture schematic is taken from this one. There is a presentation available on the website. What is done here? Let me first explain the theory. This is the most common type separator. At any given accelerating voltage V, suppose, all the singly charged ions are provided some kinetic energy, and that is given by this electronic charge E multiplied by the accelerating voltage V must be equal to kinetic energy of the charged species, that is half mv square. Now, if you allow this charge accelerated species to pass through a magnetic field, which is shown here, this is the magnet, you see, the charged ions will experience a magnetic force, and this magnetic force is given by HEV, where H is the magnetic field strength. So, therefore, this is balanced, this magnetic force is balanced by the centrifugal force, obviously. So, that means we can write down HEV must be equal to centrifugal force, that is mv square by r. So, you get m by E is equal to h square r square by 2v, straightforward, and this is what is the classical equation which allows us to separate different PCCs with different values of m by E ratio. As you can see, depending on the different m by E ratio, if you keep h and v constant, r will change. So, therefore, lighter ones will come as a smaller r, and heavier ones come as a very large r. So, that is how actually you can differentiate between different PCs, charge PCs with different m by E ratios. It is very simple actually. In fact, the first you charge, then accelerate, and then accelerated charge are passed through a magnetic field and it separates out. That is how it is done. So, we are focusing with a single magnets, that is why it is called a single focus mass spectrometer. Remember, this is actually how we can actually separate the ions very easily, and subsequently what all techniques, several techniques you will see, they are actually modification of this one. So, it is very high resolution, its instrument gives actually, it gives you quite substantially high resolutions in the sense of ppm level detection possible. In this type of instrument, two ion beams from independent sources passes side by side through a common mass analyzer and detected by separate collectors. This is used to compare sample with a standard array through different ionizing condition. Resolving power is order of 30,000 sorry. Such resolving capability enables high molecular weight fragments which differ only by one mass unit. That means if there are two species with a mass unit difference of 30,000 and 29,999, still we can detect by this. That is what the resolution of this instrument. Next one, which is also widely used quite some time, is known as double focus mass spectrometer. What is double focus mass spectrometer? Well, single focus mass spectrometer you have seen, here we are using two focusing magnets. So you have you can see this is the lens, and then basically ion sources come through this is the ion source, and then it passes through a lens, there is a source slit, and then there is a magnetic field, it just basically magnetic sector, it just separate these ions out or filters the masses, and then it passes through this single mass whichever is basically passing through this radius which is matching with the slit will pass through to go to the detector. So if you change the slit little bit, or if you change the magnetic moment, that is H value, you can allow either this one or this one or this one to pass through the slit and be detected. That is the advantage as compared to the first technique, the single focus mass spectrometer. It has very much better resolution than the single focus mass spectrometer. That is mainly because there is an extra element like this possible here. That is why it is called a double focus, because first you are focusing with the magnetic sector, then you are focusing with the electrostatic sector, and that is how actually you can detect very precisely each and every atom charge species. This is again taken from one of the websites which is available on the internet. Next one, and probably one of the best one, is quadrupole mass analyzer. The reason I am saying this is the best one, because it allows us even better measurement than single focus or double focus magnetic spectrometer. Well, it makes use of a combination of direct current and rare frequency electric field applied to 4 parallel rods. Remember, it is applied to 4 parallel rods to separate ions according to their mass by charge ratio. So we are using direct current as well as rare frequency electric field and using 4 parallel rods. These are all, that is why it is called quadrupole, to separate the ions. What is done here? This is taken from Wickerman's book. So you have a sample, you create ions by different ionization techniques, and then you have 1, 2, these are actually filters, okay, post or P filters quadrupole. They are the 4 important ones, and then it passes through this region where this quadrupole actually separates the ions depending its mass to charge ratio and detected. You can see here this is DC voltage, this is the RF voltage you can apply, and repeat, these are the 4 probes of different dimensions. Now if I plot the movement of the ions, you can see here this has the 2 parameters A and Q. Q is the charge and A is basically the distance between the quadrupoles. So if you can see the plots, you see here there are different regions. This is U by B constant, low resolution, U by B constant, high resolution, okay, U by B, U and B. This is U minus delta U by V constant by constant resolutions, and this is what is the region of stability. So that means we can change U and V in such a way, U is basically DC voltage and V is the RF voltage magnitude. So by playing around these two, we can actually get into this region of stability, and that is the region one which you need to work. Obviously, if you want to work with U by B constant high resolution region, you can do that, or you can want to work with constant resolution, you can do that depending on the systems on which you are working on. So, as you see here, this gives us many possibilities of changing the conditions and do the measurements. Fourth technique which is important is ion trap mass spectrometer. As the name suggests, is basically traps. As you know, Paul actually got Nobel Prize because of ion trap mass, the technique availability. I have told you that in 1983. Ion beam currents are normally of the order of 10 to the minus 15 to minus 19 amperes, so very small. That is because the number of ions present in the source beam is very small. This technique generally employed ion collectors, and they are actually photographic plates or electron multipliers. So, what is done here? You have basically filament, and which actually creates ions, a charged species, and then we have this kind of ring electrodes which basically collects or traps these ions, and after that we can actually use this mass spectroscopy or use this kind of single focus or double focus or quadruple, and then we can actually analyze these ions by mass by charge ratio, and finally we can detect them using transducer. That is why we did. So, basically preparation wise is different, distinctly different from the other three techniques. This is normally not used much except for few specific applications. This one is also taken from this website. Well, the last technique which I am talking about is what is known as time of flight mass spectrometer. The schematic shows the technique actually. What is here? You look at it very carefully. You have an ion gun which creates or ionizes the pieces, and then there is a pulsing action. It can pulse actually, ion gun can obviously pulse like a laser beam, and then you can focus this. It also allows, the ion gun also allows to raster like SEM the ions, and then once it falls on the target, it creates ions from the surface, and then it passes through this extractor which extract the ions which are coming from this because of this ionization due to ion gun. That means we are creating a secondary ions actually, and then basically ion mirrors, which is nothing but a quadruple detector or maybe a time of flight detector. It basically separates the ion, and detector detects and gives you the spectrum. Correct. So, many cases as you create more ions, so you have to have an electron flight gun, otherwise charge balance will not be there in the sample surface. In a more sophisticated design, the time of flight analyzers corrects for the small differences in initial energy and angle in order to achieve high mass resolutions. It is a combination of linear drift paths, electrostatic sectors or the ion mirrors which are used, and results are actually comes with the mass resolutions that of the above 10,000 can be achieved. Advantage of this technique about the quadrupole and the magnetic sector type is that extremely high transmission, parallel detection of all masses, and unlimited mass range is possible. Yes, because it does not use, because what we are doing is basically time of flight measurements. How much time a mass takes to fly or move in a particular distance, and depending on that we can differentiate among different pieces. We are not using the exactly m by z ratio. So, let me just give you the mathematics of it. Pulses of secondary ions are accelerated. As you know, ion gun creates secondary ions, and pulses of secondary ions are accelerated to give to a given potential which is of the order of certain kilo electron volts 3 to 8, such that all the ions possess the same kinetic energies. Then these ions are allowed to drift through a field free space. Remember, after these ions are accelerated secondary ions, they are allowed to pass through a drift through a field free space. We are not applying any magnetic electrostatic field before reaching a detector, and when it passes through, because they have the same kinetic energy m by mv square, but velocities will be different. So, because of this, masses are different, velocities will be different. Because of this, the time it takes to move a length will be given by L m by 2 z v half. L is basically the length, path length, flight path length, m is the mass, z is the ionic charge, and v is the accelerating voltage. So as you can see, depending on m by z values, if for even L and V are constant, T will be different, and by knowing the different times we can actually separate these ions very easily. This is actually widely used now what the whole worldwide technique, and it has many advantages. Now if I go back to the previous slide, that is what is done. In the ion mirror, between the extractor and ion bearer, what is done is that this secondary ions having a same kinetic energy travels or drifts through a path of certain length may be this much, and gets separated out. And then we can plot, I will show you the plots also later, we can plot and get idea of that. So this is I am going to discuss in detail when I come to SIMS. So but to give you some idea, in a static SIM experiments, it actually analyzes the original non-modified surface compositions, uses time of flight measurements, and it basically is a quasi non-destructive surface analysis because it uses very low ion dose. Well, as I have talked about a lot of different magnetic focus, like single mirror magnetic focus or double magnetic focus or even quadrupole, let me just give you some idea about what a radius of curvature means, how does the ions actually get curved. Radius of curvature are of any ions of distinct m by z ratio travelling through a perpendicular magnetic field B after it has been accelerated by certain potential is nothing but 1 by B within bracket 2 mv by z to the power half. So if B is constant, it depends on the m by z. So the travel, ions actually travelling, as I go back I can, ions which are travelling at different radius, that will depend on m by v. So that is what actually used in this technique. Now after giving a huge introduction, lot of things I have talked about it, about the mass spectroscopy. Let me just get into details of the secondary ion mass spectroscopy. Although there are many things which are similar, but distinct things, the things which are distinct in SIMS as compared to this MS or mass spectroscopy is to be known to you very clearly. SIMS per se is a surface analysis technique, remember this. Mass spectroscopy may not be surface analysis technique. SIMS is basically a specifically surface analysis technique. It is used to characterize surface and subsurface regions of any material. That is actually what makes SIMS very popular. Even if you have a thin film on the surface of any material, you can analyze it to the precision of SIMS. It can give you ppm level precision. It effectively employs the mass spectrometry, what I discussed, of ionized particles which are emitted when a solid surface is bombarded by energetic particles. The schematic diagram on the right side to you is showing this picture. We have an incident ion source, it can be ion which I am going to discuss, any ion. In fact, this is what is our one of the things which I will discuss. Incident ions which can be either cesium ion or it can be oxygen ion or it can be other ions, but mostly cesium and oxygen ions are used, which are actually accelerated with certain kinetic energies, and then they are allowed to fall on the surface of a sample or a target, and once it comes, it creates a cascade of events in which emitted secondary ions from the samples are emitted. So primary particles are mostly ions, or either it can be protons also, or it can be neutral pieces also, it can be charged pieces also, but they are actually primary ions, and they invade there actually the sample surface and creates the ions. Now if I have to tell you about that, in a secondary SIMS, the primary ion sources are actually created by instrument called duoplasmaton, is known as duoplasmaton. It is the one which can create different ions, and it can actually it can create ions like different gases. Oxygen is basically commonly used in the SIMS. oxygen can comes as a O minus or O2 plus, or it can comes even O2 minus. We are surprised, what are these? O minus is basically when oxygen, all the oxygens are tripped. O2 plus is that means one oxygen is tripped. O2 minus is one extra electron is added. So that's why, so that means we can have positive charge ion, negatively charged ion, and also heavier charge ion, O2 minus and O minus. So we can create all kinds of charge pieces, and then these primary ions are allowed to fall on the sample surface to create this. So you know, but this O2 O minus ion is the most abundant species used, while positive ions are also used. If you have an insulating material, then we have to use O minus ion, because otherwise there will be charge built up on the surface. And the second type of SIMS also uses something known as cesium ion. It is to enhance actually yield of this electronegative elements like carbon, oxygen, or even sulfur, because they are very low atomic mass elements. We use CS GaN, cesium GaNs actually operate in the positive modes to create the CS plus ions. Generally CS beams are smaller and then generated by doplasmaton. Doplasmaton creates oxygen ions basically, and you can create others, but mostly. And so, but the CS GaNs are basically much finer, and it can sputter. Basically this is nothing but sputtering process. You are bringing in primary ions and sputtering. You can sputter actually more material effectively because of their greater mass, and it is normally used to extensively measure the different isotopes. And when you use insulating material, you can always use CS plus beams. As you know, most of these things are surface ionization process, so therefore it leads to heating up of the samples, and sometimes it can create other problems also. So let me just give you idea about what is the collision, what does the collision happens. This is nothing but a collision cascade. A sample is prepared in a vacuum, and when you put a primary ions of this much energy, 3 to 20 kilovolts, it causes a collision cascade among the surface atoms, and between 1 and 10 are actually ions are created. This is obviously sputtering, but sputtering by using primary ions. Sputter yield depends on the nature of the sample also. Now what is collision cascade? If you have an incident primary beam coming at an angle theta with respect to the surface normal, this can create large, you can see, number of secondary ions. So one can create other can create another one, and then goes on. That is what is called cascade, collision cascade, and this leads to cascade mixing in the sample. So initial depths will be transient one, and then finally when the cascade is stabilized, this kind of origin of the surface ions is called steady state depths. So therefore measurements from the steady state depths are actually much better than the transient one. So we have discussed about collision cascade in a interaction of primary ions with the sample surface. To give you a better idea of that, I am just showing you the schematic picture. This one is showing you the atoms and the primary and the secondary ions. As you see here, the different different atoms in the sample surface is shown here like this, sorry, and these are known as target atoms. These are known as target atoms, these ones, okay, which I marked, and then you have a surface atoms which are marked in blue, and you will always have a overlay layer which contains contaminations. So primary ions which are coming at a very high energy, they come and hit, suppose this is a primary ion comes and hit this atom, and this atom is rejected or moved. This atom has many choices, it can either go and hit this or this one, and subsequently those atoms which are hit can also hit the other atoms, and that is how this cascade is created, and finally it hits the surface atoms and the secondary ions comes into picture, and these are all secondary ions as shown there. So, of these ejected atoms, some are ionized, usually less than 10%, and these are all called secondary ions. The matrix of a sample must be known to accurately determine the elemental concentrations, as ionization yields can vary very much as order of 3 orders of magnitude between nearly identical atomic sputtering yields. Secondary ions can then be analyzed using mass spectroscopy, which I have discussed. Now, there are many primary ion sources in SIMS. The most widely used, as I discussed, is oxygen and the cesium, but one can use also electron as an ion a source. You can have a high current density of electrons, like to ionize basically argon or xenon. You can always use plasma. Plasma is nothing but it's a ionic charge gas. It is a high pressure gas, high electron density, and plasma is formed, normally is formed in dual plasmaton, which I discussed. You can always have an air frequency for oxygen and argon. You can also have something known as surface ionization. Ion emission is thermally stimulated by warming an absorbed layer of cesium on a high working metal like iridium. You can do that because the thermal simulation can always lead to surface ionization. Easiest but the best one is the field emission, field ionization. You can strip off electrons from the source atoms very neatly by using a high local electric field. For that you need a very fine tip, and this is what done in atom probe, or you can have a liquid metal, typically gallium, on a tungsten tip. So, these all can be, any of these things can be used, other than even also you can use cesium and oxygen, as I said. Now, what is basically the sputtering process? All this is a collision cascade, but it is basically a sputtering. The process of sputtering is described by the principle of classical mechanics by binary collisions of primary ions with a single target atoms. Depending on the energy range of the primary particles or primary ions, elastic and inelastic scattering both are possible. The dominating interactions in the kiloelectron volt range are elastic collisions. They can be described by a parameter which is well known as a nuclear stopping power in the literature, and this is defined as the energy loss of the primary particles per path length. So, if an primary particles are losing energy because of the sputtering process, we can always take d by dx as a parameter to determine the interaction between the primary ions and the secondary ions, and this is what is known as nuclear stopping power. The number of inelastic collision increases with the rising energy, as is usual. Inelastic scattering normally dominates if you have energies in the million electron volts. So, that is why very high energy ones actually leads to a lot of inelastic scattering, which are not good. In those cases, corresponding value to describe the interaction is known as electronic stopping power, and this is known as d by dx E. Nuclear stopping power actually contributes to the collision cascade. These are the two effective ways of basically terming this sputtering process. Now, it is also important to know the primary ion sputter yield, where how many primary ions are actually, when they are sputtering, how many secondary ions are created per unit primary ion. This is taken from Bickerman's book. This is a plot of yield versus energy. As you see, yields varies from -3 to 10 + 2. That means it varies from very low value to 1000, and these are the different data from helium, xenon, argon, or some theoretical calculation or argon theoretical calculation. You see here, sputtering yield actually varies from 10 to the -2 to 10 to the ⁻1, that is 10. It does not increases much. Yield means basically number of secondary ions created per primary ions. So, that means when it is 10, one primary ion creates 10 secondary ions. When it is 10 to the -2, that means to create one secondary ion you need 100 primary ions. So, as you see, as the energy increases, sputtering yield increases. So, if you normally we can use from 10 to 100, 150, 200 electron volts as the energy. Sometimes people use 3 to 10 also. This is also not bad. You can see in this window also you have something like 5 to 6 secondary ions per unit primary ions can be created. Well, obviously as I said, O2 plus, O minus, O2 minus ions are used. If you use that, we can actually create secondary ions if we use this as a primary ion. So, positive secondary ion yields when you have O2 plus bombardment is plotted here as a function of atomic number. If you see for elements like nitrogen, sulfur, tellurium, gold, platinum, very low, log to the power actually 3, but if you go to this one, magnesium, calcium, palladium, manganese, iron, these sets, it is very high. I plus is of the order 10 to the power 4, 5. So therefore, the amount of yield or amount of the secondary ions created when you have O2 plus bombardment is good for this kind of elements, not for other ones. If you use CS plus bombardment, what happens? This is M minus plus M plus ions plus atomic number. As you see here, this is taken from this paper in analytical chemistry from American Chemical Society. If you see here, 0 yield, 0 log 0 is basically means 1. So is above this, these are good. So therefore called carbon, oxygen, sulfur, silicon, phosphorus, arsenic, selenium, germanium, to some extent silver, antimony, tellurium, iridium, platinum and gold, cesium is good. But for these metals like iron, aluminum, magnesium, zirconium, tungsten, probably oxygen 2 plus ion is better. That is what is shown here. So that is why CS and the O2 plus, they can complement each other as a primary beam to create good yield of the secondary ions. And this is what is I am showing in a periodic table, secondary ion yields when a primary beams like that. The factors affecting the secondary ionization efficiency seems are oxygen bombardment increases with the yield of positive ions, cesium bombardment yield of negative ions, as you see. The increases can range up to 4 order of magnitudes. The yellow ones basically are O2 positive secondary ions and green ones are basically CS positive ions lead to negative secondation. If you see here this one, this lithium, sodium and also this set of atoms or this set of actually elements are good for oxygen plus positive ions to create secondary ion yields. On the other, and they are also good. On the other hand, there are set of atoms like this, even carbon, nitrogen, all this group here, oxygen, fluorine, chlorine, silicon, phosphorus, all they are actually good for, will be large amount of secondary yields will possible when you use CS plus primary ions. Well, so that means if I consider positive and negative ion yield processes, then I need to tell you that oxygen enhancement process occurs as a result of metal oxygen bonds in an oxygen rich zone. So therefore, those are metals which will form very good metal oxygen bonds, they will form better secondary ion yields. When these bonds break in an ion emission process, oxygen becomes negatively charged because of its high electron affinity, which favors electron capture, and its high ionization potential eliminates the positive charging. So metal is left with a positive charge then. So oxygen beam sputtering increases the concentration of the oxygen in the surface layer. That is possible because oxygen actually first bonds with metal and forms this bond, then its bond breaks, oxygen ion remains there, metal ion comes out. Enhanced negative ion yield is normally produced by the cesium bombardment, and this can be explained by work function that are reduced by implantation of cesium into the sample surface. More secondary electrons are excited of the sample potential barrier, and this leads to increased availability of electrons, leading to increased negative ion formation. So as you clearly understood now that oxygen bombardment will lead to positive ion creation, cesium bombardment lead to negative ion creation. So therefore, the metals in which positive ion creations are easier, all metals actually positive ion creation is easier, but oxygen absorption is easier, it is better to use oxygen enhancement, and other things, metalloids or even some other metals, specific metal like copper, other things here I have shown you, zinc, copper, silver, gold, and the heavy metals like bismuth, metalloid like bismuth, antimony, tin, tellurium, you can use cesium. Obviously, secondary ion yields depends on elements, type of elements which you are dealing with. Secondary ionization efficiency is very well defined things. It is nothing but a fraction of the sputter ions that become ionized. You have large number of sputter atoms, only 10 or 15% atoms becomes ionized. So that fraction is known as secondary ion yield. As you know, ion yield vary over orders of magnitudes for different various elements. That means there is an elemental effect. The most obvious influence is on the ion yields are basically ionization potential of the positive ions. Otherwise, if the ionization potential is very high, it will sputter an atom, not an ion. And also electron affinity of the negatively charged ions. For example, this figure actually shows a logarithmic positive ion yield as a function of ionization potential. Ion yields are relative to the silicon in a silicon matrix with oxygen sputtering. So what you see here, cesium, ruthenium and the rubidium and potassium has a very high ionization yield, whereas neodymium, neon and helium has a very low ion yield. In fact, fluorine is also in a borderline case. So ionization potential is high, means less secondary ion yield, ionization potential low, more secondary ion yields. That is obvious, because then only we can create more ions by removing the electrons. So that is actually how the secondary ion yields depends on. Not only that, secondary ion can have different energies, because we can create secondary ions, but whether they will be able to be traveling to a detector or not, whether we will be able to collect them or not, depends on their energy distributions. Sputtering process produces secondary ions with a range of kinetic energies. Energy distributions are distinctly different for atomic and molecular ions. Molecular ions have always relatively narrow transitional energy distribution, because the kinetic energy is in the internal vibration and rotational modes, whereas atomic ions have kinetic energy in transitional modes. So following this figure actually showing us mono, di and triatomic ions. As you see, relative intensities of the monoatomic ions are much larger than bi and triatomic ions, di and diatomic atoms. That is understandable, because as the number of ions increases, number of actually charge increases, it is they will have less probability to presence. So as you see, this is a plot of relative intensity versus energy. So only in a particular energy window between about 2 to 8 volts, you have a relatively high intensity of all the different types of ions. So I have given you a lot of idea about primary ions, sputtering, yield of secondary ions, and also the factors which control the secondary ion yield. Let me just give you some idea about how a SIM spectrum look like. SIM spectrum can be plotted in two ways. First one is shown at the top, which is nothing but a plot between intensity versus mass to charge ratio. One can actually scan in B and V, that is magnetic field or voltage, static electric field applied to sweep masses across a single detector. As you see here, this is fluorine ion, this is fluorine 2 ion, this is CF3 ion, this is C2F3 ion. We can distinctly difference between these negatively charged ions depending on this mass to charge ratio. Not only that, we can even quantitatively calculate from these intensities how much of 19 mass by charge mass actually fluorine ions are present, or the double ions are present, CF3 or C3F3 minus ions are present or not. This is one way of plotting the data. Other way of plotting the data is to plot the different masses into multiple cups without changing the B and V. In this case, we are changing B and V in the top picture, so that we can sweep all the masses. Here we are not changing B and V, we are basically have different masses as a cups. This is relative ion current versus magnetic field strength, that is B. As you see here, at any constant B value, you have different relative ions for 88, 87, 86 atomic species. So you get a cup like picture whenever you plot for the whole magnetic fields, for the values of a large range of magnetic fields. So you can basically get a cup, and this cups gives you different charge species. If you plot, basically SIMS can measure starting from lithium to uranium. So if you want to show the relative intensities of the peaks for different metals, this is the best one. Here I am showing you intensity versus mass to charge ratio. What you see here is basically starting from lithium to uranium, the m/z values and intensities. So as you see here, certain the m/z, if the m/z is lower than actually certain areas like this one, you have very high intensity of your 10 to the power 6, 10 to the 5 counts per second. Whereas here if its m/z is very high, lead, thorium, uranium, even higher numbers. So you can see here the yield is, sorry, the intensity is low. You can actually see even that intensity is low for even barium compounds also. So that means the intensity of these secondary ions, which is detected by detector, depends also on the mass by charge ratio. So in a secondary ion mass spectroscopy, what all things are there? Obviously I have discussed about the ion source, primary ions. You need a sample, primary ions comes and hit the sample, create secondary ions. Then you have a energy analyzer or other energy grabber, which the secondary ion grabber which grabs and analyzes the energy, and these ions are then passed to the mass spectrometer, and then which separates the ions depending on m/z values, and you detect. So you can actually have a mass spectrum which I have shown you. You can also have a depth profile, which I am going to discuss. It is very important in material science, and you can actually also create an image of 2-dimensional image. Actually, truly speaking, you can create a 3-dimensional image also in a SIMS. It is so powerful technique. So this is the one I have shown you, that is why I wanted to show you this before. I show the basic overview. Now I am going to show you how depth profile, quantification and image formation is done. Well, as we said, these are different mass analyzer use, and the idea is to show you how their relative behavior is. If you have a quadruple mass spectrometer, you have a resolution of 10 to the power 2, 10 to the power 3, that means 100 to 1000. Mass ranges which can be detected is less than 1000. Transmission is pretty low, all the cases, but it is lowest in the quadruple. Mass detection is sequential, 1 by 1. Sensitivity in a scale of 10,000 it is 1. If you use a magnetic sector, that curve magnetic sector I have shown you, it is a resolution 10 to the power 4 at 10,000. Mass ranges can be very high, that means you can detect 10 to the power 4 and higher. Transmission is also quite high means higher than the quadruple, 0.1 to 0.5. Again measurement is sequential. Sensitivity is better than quadruple, but not very high. Best one is, that is what I said to you in the lecture, is time of flight. Time of flight has a high resolution, 10 to the power 3 or higher. It can scan mass ranges from 10 to the power 3 to 10 to the power 4. It has a very good transmission, approximately close to 1. It can detect masses parallelly, not sequentially, parallelly together. That is the advantage. And it has a very high relative sensitivity, 10 to the power 4, 10,000. So that means time of flight is very strong. So therefore you can clearly see that time of flight is the best option for us, or for the SIMS, and that is why it is widely used in the different machines. Now SIMS analysis can be done in different ways. One, the most widely used one is static SIMS, which are used to determine the surface concentration of elements and molecules without significantly altering the sample. Then you can image SIMS, that is what I said a few minutes back. Like static SIMS does not alter the sample appreciably. This mode used to generate images or maps based upon the concentration of secondary ions representing either an element or molecule. You can have also a dynamic SIMS involving the use of a much higher energy beams, primary beams, but it is used to generate normally depth profiles, not the 2-dimensional profiles. So along the depth you can measure the concentrations. In a static SIMS actually, you can use low ion flux. This means a small amount of primary ions is used to bombard the sample per unit time. Sputters have the approximately only 1/10 of an atomic monolayer, very small flux. So we use normally argon xenon ions or argon and xenon, and it has a diameter of very small, like 2 to 3 nanometers. Analysis typically requires more than 15 minutes. It generates some mass spectral data well suited for detection of the organic molecules. To give you some results, it is taken from polyethynyl methacrylate SIMS, both positive and negative SIMS data. See that you can detect actually different, I do not know whether you can see C3H5 plus, C3H5, C15H5, or this kind of DCO, C3H5 things, positive ions, and negative ions if you use like cesium or things which can create you can actually have, these are different negative ions, CH3O minus, C3OH minus, C2CH minus are these ones. So depending on the different positive and negative ions, you can actually detect all of them using these static SIMS. Fragmentation and subsequent ion formation of the sample can reveal the overall structural molecule to the mass spectroscopy is possible to do. Next one, which I have already discussed, is time of flight. Time of flight is the most notable one. Here actually you have an ion gun which can pulsed and actually raster also, and falls on the primary ions falls on the sample surface, then secondary ions are generated. You can extract the secondary ions by using extractor, and then it passes through a long distance, and during they actually extract and accelerate with the same voltage, same kinetic energies, different voltage. Kinetic energies means kinetic energy of each ions are same at the beginning, and when they travel the long distance, the time of flight varies. By this way we can detect. This is a sophisticated instrument, as I said, and used for many applications. And this is the equation I showed you. So depending on the m by z values, you can have a different time scale, and you can detect that. SIMS and time of flight operations actually very popular one. It uses it is with the extractive technique. You can remove the sample and measures the secondary ions, and then one by one layer wise removal possible, and measure the compositions one by one. So that is why it is used. So you have a sputter, time of sputter ions, and then time of flight, and then online mass spectrometer. Well, we should also know some aspect about the intensity of the species of the secondary ions, and this is basically equal to IPY alpha AQ CAT. As you see, it basically depends on primary current density, total sputter yield of the primary current. Alpha is nothing but ionization probability of the charge state cube. Ca is the fractional concentration of the element A in the matrix, and T is the instrumental transmission function. So transmission function is that's why I have shown you in the few slides before. So as you see here, this is strong function of IP and Y. That is why you discussed about the primary current, primary ions, and this sputtering yield. They actually determine, along with alpha and other factors, exactly secondary ion concentration species. Well, there are problems in using this data, because this is what is the total intensity, and this can be used to quantify, and there are problems. The problem is that Y total depends moderately on CAA. Not only that, alpha also depends strongly on CAA. So it's basically, that means I of the intensity of secondary ion is not linearly proportional to CA. There will be matrix effects. That is why sometimes it is not possible to measure exactly the quantify these things. There will be always some error involved. Well, SIMS can also be used to raster or getting, and time of flight it is done, and if you have a different path, this is the beam path, you can see here beam path follows like this. So this is nothing but electronically gated area. You can actually create a scatter, and as you raster every point you can measure the SIMS profile by time of flight, and once you do that, every point you measure, you can actually get the composition values, and by this way you can create a 3-dimensional map. Another important thing which SIMS allows you to do is the depth profile. What is it? Well, one can actually slowly remove the material from the sample surface in the depth direction, measure the concentrations. Well, the important aspect in such a case is the depth resolution. what we are showing here is the intensity or concentrations of the certain species as a function of sputtering time or the depth. As you see here, this is the 100 time intensity, which is good till certain time, then it falls off near the surface. So that means this is good in this region, not good in this region. Okay. So that is what actually can be done in a SIMS depth resolution profile. One can actually use SIMS for kind of imaging or surface imaging, because you can raster. So if you can raster, you can actually image by rastering a finely focused ion beams over a surface like this, and one can actually create mass dissolved secondary ion images. It is basically nothing but a scanning electron microscopic image, but here we are getting mass dissolved secondary images. And as you see here, if I have a beam, primary beam, which I can raster on the sample surface, and then from each point we can generate secondary ions, and measuring the secondary ion types and the yield of that and quantifying the different elements, we can actually create a map. It is just like an elemental map in a SEM. You have different peaks from different element comes, and then from a particular point, and then measuring the peak intensity, you can quantify the particular element, and you can map. This is exactly done it here, same thing. You can use, instead of a electron microscopy, using this in a secondary ion mass spectroscopy, and this is what a picture you get, colorful picture. You see here, it shows you concentration of the 3 different species. One is green, blue, and little bit red. So that means it is possible to go that. Not only that, as I said, it is possible to do depth profiling. In concentration static SIMS experiment, the dynamic ones actually, high primary dose densities can be applied in this, and it can give you successive removal of the respective top surface layers, and by occurring spectra during the sputtering, the in-depth distribution of elements and small clusters can be monitored. So as you see here, this is a volume which is sputtered slowly, and raster also obviously. So you just start from this part and then go, then you come back, do like the raster. So one surface layer is removed and you measure the composition. Then you go in the depth direction and then do the same thing, rastering, and get the distribution of elements in a 3-dimensional. Or otherwise you can actually keep the beam constant static, do not do the beam, and just sputter along a certain directions and measure the constants from the elements. Obviously I have given a lot of examples, different examples, all sorts of examples I have given. As you see here, one must know very clearly that there are very advanced measurements can be done using SIMS. This is a technique which is used extensively in material science and surface science to analyze the composition of solid surfaces and also thin films by sputtering the surface of the specimen with a focused primary ion beam and collecting and analyzing the ejected secondary ions. Secondary ions are then measured using a mass spectrometer. You can do elemental, isotropic, molecular composition of the surfaces. Actually you can measure elements from hydrogen to uranium, not hydrogen actually, you can do lithium to uranium very easily. You can actually detect element down to concentration from 1 ppm to 1 ppb. Isotope ratios can be measured. Isotope ratios means if your oxygen has 3 or 4 isotopes, what are the abundance of the isotopes can be determined normally to precision of 0.5 to 0.05%, which cannot be done by using any other techniques. You can actually do 2-dimensional ionic image measurements, ionic images which I shown you. A secondary ion leaves the surface at a point close to the original location. This enables localized analysis of a sample to be undertaken, and is a correction, is a cornerstone of the images. So not only that, you can actually have 3-dimensional ion images can be acquired by scanning or rastering the primary beam and detecting that. It requires very little sample preparation. Let me tell you, very little sample preparation, unlike in SEM on the TM, you do not require much sample preparations, and you can actually do many other things. You can actually material sputter actually, as you might be thinking, material sputter is very large here. No, sputtering is few fractions of distance of atomic layer on the surface. So sputtering is small, you don't damage very, but only once you do dynamic seems you damage the sample surface, but there are problems, and so I have just given you 3-dimensional image. Volume of the material sputter is small, I told, but it has some limitations. It is not a foolproof technique. The major limitation of this technique is that the material which is part of a sample surface, it not only consists of monoatomic ions, but also consists of molecular PCSs that in places can actually dominate the smart spectrum and making the analysis of this element impossible. This is very obvious because you have a high energy primary source, and this high energy primary source can bombard and create molecular PCSs like CH4 plus, CH3 plus, CH3 minus PCSs can be created in organic things, many others. Normally in metals it is not possible, but it can create metal complexes because cascade of these primary ion events can lead to mixing, and mixing can lead to even formation of metal complexes. Second important thing which is bad about this is this whole sputtering process, which is the main thing in a SIMS, is very poorly understood. We do not have any quantitative model so far that can accurately predict the secondary ionization process. There is no. So that actually makes us assume certain things for the secondary ion generation process, and that assumption actually makes the technique a little bit less attractive, in the sense that we do not know really how the secondary ions are actually created, what are the process. So we have no idea. We can measure the yields and other things, but we have no idea, theoretically also we cannot model it. Third thing is that to obtain a quantity information of a suitable standard, you have to have a quantitative information in a suitable standard. That is the case for everything. In a CM also EDS also requires, so measurements of these requires a standard. Third thing is that sensitivity of an element is strongly dependent on the composition of the matrix. Remember, you are putting the element in a matrix, organic matrix, liquid matrix. So it depends on the matrix. We have shown that. Even the intensity is also a function of the matrix. It is not a linear with only the element present. And also type of primary beams used. 6 standards should therefore be close to the composition of the unknown. This is particularly true for isotopic analysis. Lastly, samples which we are doing must be compatible at high vacuum. It should not degrade inside the vacuum system, because you are using a very high vacuum system, -6, -9 to -10 torr. Under that vacuum, it should not transform or should not degrade to other thing else. That is basically a big limitation for that. Otherwise, it has many advantages. And so with this, I actually close this discussion on the SIMS, and only thing I need to do is to compare these 3 techniques, surface characterization technique like XPS, Auger and the SIMS, and tell you how these techniques can be used in different things.